you see it?
Yeah, we
Okay.
see it now.
So
So
this is,
you did this with Canva,
yeah.
right? And is this, had you used Canva before?
I used it one time. It was for a class in high school, and we were doing a report on like the Constitution. And I basically made an infographic talking about the Constitution.
Uh-huh.
So,
Yeah, and so, but this looks okay. This is great. Natalie, I see what you said there, and yeah, I'll get back to you, Natalie. Exactly. It's not a speech. It's more like casual, whatever you can tell. So, go ahead, Thomas.
okay. I gave it the title Project Exponential Training in COVID-19 Pandemic.
Uh-huh.
Here's the background. I included a little picture of COVID.
That is so. Did you get that picture in CDC or?
I went over here to photos, and then
Ah,
you can search
okay,
online for a
okay.
picture.
Yeah, so just a little note that it's supposed to be a virus, and the virus looks like a sphere or
Yeah.
like a little ball. And then on the surface, there are little thingies there. And maybe I should prepare something for Thursday and kind of give a little. So that's usually the stuff that's on the surface is important because that's how the virus gets attached to a cell, and that's how the virus gets released from that cell. And when there are treatments, unlike antibiotics, the antibiotics are things that are meant to go and kill bacteria. It doesn't work like that for well, maybe the antivirals are in the sense to interfere. Sometimes those treatments are not exactly killing virus, but they interfere with that surface, with those shapes, and that interferes with the life cycle of the virus to attach or detach from wherever they go. All right, go ahead. Sorry that I interrupted you.
Okay. Uh, Here's the background. What is COVID-19? And I used the CDC website to basically come up with this little paragraph stating that's caused by SARS-CoV-2. It can spread easily through the respiratory system. Symptoms may appear 2 to 14 days after exposure. And then I included a list of the symptoms like fever, chills, coughing, shortness of breath, difficulty breathing, fatigue, body aches, etc. I basically just looked at the symptoms and just started listing them.
Mm-hmm.
And then I included those who were at an increased risk for the disease, such as the elderly. Sorry, I can't talk today. The elderly or those with medical conditions pre-existing before infection.
Right. I think one of those medical pre-existing conditions could be diabetes.
Yes,
And
diabetes, or like if you have issues with like the respiratory system already, like you're susceptible to pneumonia or something,
mm-hmm.
it can cause some trouble.
Okay.
But infection can cause more serious illnesses, and some people, like it can aggravate certain respiratory illnesses you already have if you have one already. Um, so it's best to avoid being exposed. And then down here, I chose the template, but I forgot to check and make sure there was enough sections. So I was gonna originally do it all vertically and then put like pictures over here
Mm-hmm.
for this. However, I noticed that it was too short for that. So I just put the mathematical over here, like what was used for the
Mm-hmm.
data, and then explain where the data set's from
Yeah.
over here. So I guess adapt and,
Yeah. Yeah.
handle that.
Yeah. Yeah.
But I got from like the New York Times thing where you click the state you got, and then you see all the different numbers.
The state, what was your state again?
Texas.
Texas. Okay. So you scroll down. So you have the on the right,
Yeah,
that's
this is
the
the entire.
complete original data. So no log transformation is the original data from, it's like how many points do you have there? Like 250 or something?
Something like that. Yeah.
Yeah, so you did go from the first point they had in March all the way to
Yeah.
more than September, right? Maybe
Yeah.
October. Okay. Yeah.
Um, but these rectangles were actually a lot difficult to figure out how to do until I figured out you could use the elements over here.
All
So
right.
that's how I did that.
Okay. Okay.
Um,
Yeah.
up here.
So you could sometimes that part of editing the figures, if your data in Desmos, like which was plotted there in green, if that's a PNG, and you had something like Paint or even PowerPoint,
Uh,
you can edit in PowerPoint, like throwing those rectangles and annotating in PowerPoint, sometimes a little more user friendly. But then you would have to generate like a screenshot or something of that PowerPoint thingy, and then you would
yeah.
have to insert that here.
Yeah.
But yeah, but it's great that you use the what was that again? The elements on the
Yeah. The
left.
elements, they
Okay.
basically come with all these shapes. And then I scrolled down and I found these hollowed out rectangles. I'm like, okay, that'll work.
Yeah. Okay. So you have your three subsets are from
Yeah.
day 50 to 100. The second one from
Yeah.
um,
That's listed up here in this paragraph 50 to 100, 150 to 175. And then the last one was 190 to 224.
uh-huh. Okay.
And then here's each of the subsets. I accidentally included residuals for the first one.
Yeah.
So that's why there's a
No,
bunch of
that's
blue dots
fine.
here.
Yeah, that's fine. So the residuals are the differences between what you see there in black and what you see there in green. So at each time point, there will be one corresponding value on the curve and then that data value. And so they take the difference. Sometimes you see that when maybe it's the data minus the graph, because when you see the green under the curve, the residuals are negative.
Yeah.
And the other portion where the green is above the curve, the residuals are positive. So that's fine. In Desmos, when you see that, you have to basically click. You know how you click and then click to
Yeah.
have one graph appear and disappear? That's you have to go where the data, where the residuals are and click on it, and then it will go away. But this looks great. So you use in Desmos the direct, you didn't do the two steps of log data and linear regression and then going back to the exponential. You did like what you have there at the top, y1, well, kind of at the top, next on the right, next to the first graph.
Yeah.
Yeah, y1 and then tilde a exp. So you use that. That's
Yeah.
where your y1 was your original data, and where your x1. So the y1 stores the number of cases, and the x1 stores the day number. And since you started with 50, so you're using that form that has x minus x0, and in this
Yeah.
case, x0 is 50. And so Desmos came back with the value of A should be about 10,000, and here the value of K is 0.0345,
Yeah.
right? That's, and so that 10,000 should be close to your first measurement for day 50, the number of cases day 50.
Yeah.
So
And
maybe it's a
then
little less,
the
but
doubling time is
the
down here.
doubling time, so what was in this case your doubling time is about 20,
Yeah. About 20.
about 20 for the first 50 days. Well, the first subset. What was the doubling time for the second subset?
The second subset was about 30 days. Come in. There.
So from 20 to 30, and then the last one.
The last one was 103 days.
So 20 to 30 to 100, right?
Yeah.
That's what you're seeing on those windows you have there at the right.
Yeah.
And so the doubling time, as I think you explained it somewhere in there, is when you see that doubling time being short, then we're in trouble. And if it stretches, then we're still in trouble, but less trouble, right? So if they say doling time of 2 days, holy crap, that means every 48 hours we have double of the number of cases, right? So if it's for 2 days, it's like short. 20 days is, I mean, it's almost 3 weeks, right? So, and of course, Texas is massive, right? So Texas is a state, it's a really large state. So definitely, also, if you were just going to compare the Ks, the values of K alone, then you would see a progression here from, let me see if I can annotate in your screen, which I believe I can. So yeah, that looks too, I don't know if an arrow is there. Like, here's what I'm, so there is like the slope on that first thingy there, and then maybe another slope here. I need to choose another colors. You're not really seeing that color. Like there, and then another slope. So in a way, the formula of the doubling time is like inversely proportional to the slope. So the slope, things were worst at the beginning, according to this. It's kind of hard to tell, because I would say the slope in the second subset is probably more steep than the slope on the first one.
Yeah.
But this also looks different. That's not really the slope here. That those values of K are the slopes in the logarithmic scale. So that could also be, yeah. I mean, right now the comparison is valid just using the doubling time, which is still making use of some form. The doubling time is like a transformation on K, and it's a transformation of the order like 1 over, so yeah. But this is, anything else you'd like to add? Any comment?
Not really, other than like here's my resources that I got all this information from.
Yeah. And yeah, so this is great, Thomas. This is exactly, I think this is very useful. I'm gonna see if your peers have any comments. So right. Patrick, let's see, you also use Canva?
Yes, I did.
Okay, and was it your first time?
Yes, it was.
Okay, so I can tell you that I'm not like super, my wife uses it a lot. She's like a master of Canva. I'm a novice. So, but I, to some extent, it's a little bit like using PowerPoint, and it requires a little patience. It also seems that if you find a template that you found one where you have, right now, this is one page, but it kind of goes down, right? So, so what was your state is New Hampshire, and
Yep.
what we see there at the top.
This was the total cases in New Hampshire, and then from that, I picked 3 subsets from 16 to 34, 90 to 110, and 130 to 150.
So let me try to do something. Let me see if I can put this rectangle. So 16 to 34. So that would be somewhere in there, right?
Yep.
And then 90
to 110. Be up
somewhere
here.
in there. And then the last one is 130
to 150.
Something like this, more or less. So it's interesting because in New Hampshire, It doesn't seem like an exponentially growing curve everywhere, right? When you look at that complete data set, there are portions like between 20 and 50, maybe between 20 and 80. It looks pretty linear there.
Yeah.
And something happened there. Maybe that was what you, around 110, there's like a shift. Like it was growing and then it shifts to grow in a different fashion. Yeah. And what is the last value that you have there?
130 to 150.
Yeah, but at the in your last data point in the complete data, like what's the highest level of total cases? Is still under, is that 80,000 or 8,000? Like your vertical axis, what's the largest value in your vertical axis?
It is just below 8,000.
8,000. See, wow, 8,000.
Yeah.
I mean, Tennessee has like 300,000. I mean, I remember when Tennessee was in the thousands like that, 6,000, 5,000, 6,000, under 10,000. And now we are more than 300,000. So, however, New Hampshire doesn't have 2 time zones. New Hampshire is all Eastern time. It's not Eastern and Central like our state. Yeah, so.
I was trying to pull up the table real quick to see. Yeah, the last one I had 7,861.
Yeah, I hope they keep it like that under control. Great. And so you went down there and you transformed the data for each subset, and then you did the linear regression for each subset. There is, what did you use to write the equations? Do you have there on the left?
I used Microsoft Word.
Microsoft Word, and then you pasted it, like copy and pasted, or?
So it was a little tricky. It didn't like when I copy and pasted it. So I actually saved them as pictures.
Images, and then you inserted the images. Great. They look really good. Small thing though, very small. In your what you wrote at y equals b0, then there b1 is the slope, right? So that slope would be what appears in the exponential. If you write b1x, then you would have there b1 times x0 in that expression you have in the below. And if you
Okay.
have b0, then that would be e to the b0. Now, if you rewrite the y as y equals b plus k times x, then that's exactly what you have below, with the difference of having that symbol on top of each letter. This, you don't have to change this. I'm just I mean,
Right.
basically the message is the slope in the linear regression will be the argument of the exponential. So when we say exponential of something, like the input of the exponential is going to have that slope as part of the input of the exponential, the input argument. Okay, so then you have the, so I guess one thing that is very clear from your picture on the right there in the middle is if you compare the slope, right? Like the green slope should be the steepest.
Yep.
And then is it like green, orange, and purple? Like you would go super steep, less steep, and almost flat, like almost slope equal to 0, almost in that order. And that should be, oh, great. So when,
sorry, my headset died.
oh, scroll down. So you have the corresponding exponential best fits there corresponding to the green, orange. And so, and you could argue that that green subset in logarithmic scale looks very steep, very linear, very steep, but here it looks very sharp, growing exponentially, the green. And something weird happens with the orange thing. I think there is a change there, a little bit of a shift. And so what is the doubling time for each corresponding subset?
So the doubling time for the green one was just 4 days, just above 4 days. For 90 to 110 was 77. And by the time you make it to 130 to 150, you're up to 158 days.
Yeah. So do you think those numbers make sense to you? Like, do they reflect what do those numbers tell you?
Tells you how long it would take for that initial amount at like 130 to double.
Yeah.
Right?
Yeah. Yeah. But it takes shorter to double, just 4 days, while the middle set, it takes a lot longer to double. So going from 4 days to basically 78 days, right? 78 days, what? It's like 2 months,
Yeah.
2.5 months or something. So that may be, and then the last subset is like 160, I mean 158 days.
Yeah.
It takes even longer. So that seems like maybe overly optimistic, but that could be the it could be a reflection of some measures. Like, I think what you have there is a quantification of that effect of flattening the curve. That flattening the curve is referring to, it's not exactly a curve we have here, but flattening is slow down, slow the spread down, like interfere with the spread, make it so that the virus is not spreading as fast, right?
Yep.
And by seeing how those doubling times are stretching longer and longer and longer in this sample of 3, you're seeing a quantification of this may be reflecting that some of the control measures in that state are working, because or they, at least those times, they seem to really, I mean, it is clear in your green picture, your dash curve is what would have happened growing exponentially. It's hard to see in that resolution, but you see it's almost vertical.
Right.
That so if it had stayed with that value of k, then it would just, in a short period, things would have become really, really difficult, right? But it didn't. It kind of changed. And so that manipulation has to do with the, I don't know, masks, facial shields, social distancing, so a number of things.
Any of the safety measures they put in place?
I would say that this would suggest that, I mean, it would be interesting if you could find, we'll go to the original data set again.
The original?
Yeah, on the top. Yeah, there are certain days there that you selected. I mean, I guess you selected these windows for a reason, but if you were gonna find that something remarkably happened different between like the first month and the third month, like day 34 and day 90, if somewhere in between, you know, you found some reports, some news. And so, Natalie, what did you use to create your delivery?
I use PowerPoint since I've used PowerPoint for like 10 years.
Right. But you use PowerPoint in not as a presentation, but you use it with the mode of like infographic, right? The vertical.
Yeah.
Yeah. Okay, this looks great. And what we're seeing here is not a PDF, it's the actual PowerPoint original file. So just make sure that all your images are what do you call it? That they're public or open or something like that. The image PowerPoint also has images, right? Like, where did you get that first one that's next to Kentucky?
This one, I think I got it from, like, if you go to, like, insert, and then it'll say, like, smart images or something.
Right.
Smart something. Basically, like, you can look it up, search it from PowerPoint's list of, like, ones that they already have. You don't have to go to Google and everything.
Right, exactly. Because if you go to Google, then that's a little tricky. But if it's in PowerPoint, it's fair game. Great. So go ahead.
Yeah.
Just tell us about your data set.
So, the data set. Let's see. Well, I just started
tell us
off
about your
all
your infographic.
So I just named it the COVID-19 pandemic trends, and my state was Kentucky. And I started off with just like an overview of just like some facts about the virus. I mean, of course, now there's a vaccine being flown in, but this was before that. Then I focused on like how to stop the spread, wear a mask, stay home, social distance, get tested. And I had extra space, so I just threw that in there. So then I credited the data sets, and then had what just happened? Oh my word! Okay, this was annoying. Hold on 1 second. There we go. So for the models, I put like just the basic
formulas.
Yeah, the formulas for the best fit and the doubling time. And then, so let's see. I used the colors to. Oh, there's okay. So for the first, let's see. This is the original. Day 0 to 199.
Okay.
And the average doubling time was about 39 or 40 days. So like I compared the rest of the doubling.
This is very interesting, because if you compare this graph there at the top, which is the complete graph, this is Kentucky, right? So
yes.
The graph we were looking at from Patrick, which was New Hampshire, did not have the same patterns. Like here, you fitted an exponential to the complete graph, to the complete data set. And based on this visual inspection, it looks like the exponential hits the data at most points, suggesting that there is a general trend of exponentially growing for the complete data set. And then when you go later in more details, you segment that into 3 subsets, and you're using an exponential for each, right? So, okay, so here's the first subset, 7 days from day 17 to day 37. And what did you find there?
So because the case, it was like the very beginning, and there's not many cases, so they can double very quickly. So the doubling time during like the first like 2 to 5 weeks was about 6 days, which is very quickly. But then again, I mean, there's not very many cases, so like 3 to 6, well, that's a doubling time. So
yeah.
Versus like later when it's like it takes a lot more time for it to go to like 20,000 to 40,000.
So what's the next subset from day 122 to day 146?
And and that's about a month.
That's about a month. So your first estimate was 6 days, and then it's a month. And what about the next subset?
This one was like the more recent ones, from 177 to 182, and that one's a little bit over a month, probably about like a month and a half-ish.
Yeah. But so just based on, if you were just comparing the 3 doubling time estimates, you go from 6 to 30 to 43, right? So similar to the findings that Patrick was presenting, in the sense that it seems to be really bad initially, but it seems to be increasingly better. Certainly it's better in the second subset, and it's even better in the third subset. Better in the sense the doubling time is a lot longer.
Yes.
So there could be something here related to control measures Like there could be something that state is doing, or the state implemented certain measures at specific times that may be reflected here.
Right. Yeah, I think that's it for this. Maybe. Oh. And then I just repeated what I had like at the beginning, and then I had the credible resources, and the there it is.
Right. So icon, that's fine. But your license is called CC by NCND 4.0. Yeah.
Okay. In the on the website, it had like them in like circles, except I could not get it to be the circles.
Yeah.
I even went on to like it through PowerPoint, and like you can insert the symbol, and they didn't have any of them.
No, but that's fine. It's just like, yeah, sometimes copying those icons are not what you wanted them to be.
Yeah, it didn't want to.
But the name of the license, they usually have these names with those acronyms that are kind of weird. CC is Creative Commons, by NC and ND. So this is, and then it's 4.0. So this is one of their 3 or 4 or 6 options that they had. Do you remember if this allows people to replicate?
I want to say it does, but I think they have to credit it.
Credited, right? Attribution.
I don't remember.
Yeah. Very good. Excellent. Thank you so much for sharing this with us. Let me ask your peers if anybody has a comment or a question.